So this is a 4.7 exercise. Two long and parallel straight wire A and B carries current. So we have two current. IA is equal to, I write 8.0 ampere. IB 5.0 ampere in the same direction, are separated by a distance 4 centimeter. So D is 4.0 centimeter. So 4.0 into 10 raised to minus 2 meter. Estimate the force on a 10 centimeter section of wire A. So we have formula for the force between two conducting wire. F is equal to mu 0 IA IBL upon 2 pi d. Okay, here mu 0 is 4 pi into 10 raised to minus 7. IA is 8 ampere. IB is 5 ampere, and you have given length is how much? 10 centimeter. So that is equal to 0.1 meter. So 0.1 divided by 2 pi into d, that is the 4 into 10 raised to minus 2. So here also values are such, you can cancel very easily. 2, so this is 4 2 ja, so 2 2 ja 4, 4 5 ja 20, so 20 into 0.1, so 2, okay, and minus 2 going up, so you are finally getting 2 into 10 raised to minus 5 Newton. That is your answer. And this force will be attractive since both currents are in the same direction. So again, in 4.8, a closely wound solenoid 80 centimeter long. So length of the solenoid is 0.8 meter. I write directly, and it has 5 layers of winding 400 tons each. So total number of tons is equal to 5 layers, and each has 400. So 5 4 ja 20, so 2000, and is diameter. So diameter is 1.8 centimeter. Current carries, this is diameter current. I is equal to 8.0 ampere. So this is our solution. Estimate the magnitude of B inside the solenoid near its center. So what is the magnetic field inside the solenoid? So we have one formula. Magnetic field inside the solenoid, it can be considered as a long solenoid because length is around 80 centimeter and diameter is very small. So B is equal to mu 0 small ni, and n is not given directly, so total number of turn divided by length into I. So mu 0 is 4 pi into 10 raised to minus 7. Number of turns we already calculated 2000. So 2000, and current carrying is 8 ampere. So divided by length, so 0.8. Again values are such, cancel out. So if you do it, we get it 2.5 into 10 raised to minus 2 Tesla. Sometimes we, by knowing this value, suppose I made mistake in doing calculation, I am getting very large value of the magnetic field. Then also I comes to know that somewhere I made the mistake, because it's very difficult to produce 1 Tesla field in the laboratory. Suppose I am getting +2, तो possible ના હોય તો થોડું આપણે વેરીફાઈ કરી શકીએ. So this is your answer of the question. Then a square coil of size 10 centimeter consists of 20 turns and carries a current of 12 centiampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle of 30 degree. It means that this is our coil. Okay, this is the coil 10 by 10 centimeter, 20 tons. So number of tons is equal to 20. Then each side is 10 centimeter, so is equal to 0.1 meter. Current I is equal to 12 ampere suspended. So this is the magnetic field direction. Okay, and this is the normal, you can say area vector, and this angle is given 30 degree with the direction of the uniform horizontal magnetic field of magnitude 0.8 Tesla. So B is equal to 0.8 Tesla. What is the magnitude of the torque experienced by the coil? So what is the torque? So we have formula for the torque is equal to BINA sin theta બીના sin theta. અને હું ઘણી વખત મજાકમાં કહેતો કે હવે બીના નામ જૂનું થઈ ગયું તો બાની sin theta. બાની એક હમણાં શિરીરિક આવતી એને બી ઘણો સમય થયો. તો બાની sin theta. So B is 0.8, current is 12, number of tons 20, area that is L square, so L is 0.1 square and into sin 30. So if we put all this value, then you get 12 96 96 2 192 and divided by 2 2 cancel the 0.96 જેવો figure આવશે. So you are getting 96, and that is joule, or you can say Newton meter. So this is your answer. So here you have given two moving coil meter M1 and M2 having the following particulars: R1, R2, A1, A2, N1 and N2, magnetic V1 and V2. The spring constants are identical, means spring constant K1 is equal to K2. Determine the ratio of current sensitivity and the voltage sensitivity. So we have current sensitivity. Current sensitivity phi upon I is equal to B and A upon K. So I say sensitivity of current for 1 meter is equal to B1 N1 A1 upon K1 for meter 1, and for meter 2 SI2 is equal to B2 N2 A2 upon K2. Determine the ratio, therefore SI1 upon SI2 is equal to B1 N1 A1 upon B2 and to A2, K2 upon K1 will cancel out because it will have same value. So you have given B1. Okay, so this is 42 into zero point 0.5. Sorry, I write B1. B1 is 0.25. Yes, sorry. B1 is 0.25 number of tons. I think 30. Area A1 3.6 into 10 raised to minus 3 meters square. 3 into 10 raised to minus 3 divided by, you have given 0.5 into 30 into 1.8 into 10 raised to minus, this is 3.6. 3. So if you simplify, you are getting 1.4. So this is your first answer, SI1 upon SI2. Sorry, 1 upon 1.4. 1 upon, you will get 10 upon 14. So you will get 5 by 7. Or you can find a reciprocal of that also. And voltage sensitivity is Vs is equal to N AB upon, याद करो, KRS. So Vs 2 upon Vs1 is equal to N2 A2 B2 upon K2 R2 divided by this reciprocal going up. So K1 R1 upon N1 A1 B1. So if you put all this value, this K2 K1 will cancel out. So you get 42 into 0.5 into 1.8 into 10 raised to minus 3 into 10, this R1 divided by 14, this is 14 into 30 number of tons into area 3.6 into 10 raised to minus 3, and B1 is your 0.25. So if you simplify, you will get 1. So here sensitivity, voltage sensitivity is same for both. Okay, but the current sensitivity is different. So this is answer 2 and this is your answer 1. In text it is SI2 upon SI1, so you will 7 by 5. In a chamber, a uniform magnetic field 6.5 Gauss is maintained. An electron is shot into the field with speed of 4 into 10 raised to 6 meter per second, normal to the field. Explain why the path of the electron is a circle. Determine the radius of a circular orbit. So first we discuss when a charge enters in magnetic field, it experiences a force F is equal to minus E V cross B. Okay, this force is always perpendicular to V and B both. So a trajectory forms in which F is always perpendicular to the motion. That is possible only in circular motion. Actually, I already discussed in the theory, so I not emphasize on much more on that. Just I write down whatever they explained here in during the discussion of motion of a charged particle. And now radius also, you know the formula mv upon qb, here E is equal to Q is equal to E. We substitute all this value. M is the mass of the electron, V is the velocity of the electron, E is the charge of the electron, B is the magnetic field. 6.5 Gauss you convert into Tesla, your relation also given. So if you put all this value, then this value is comes out to be 4.2 into 10 raised to minus 2. So you can say that 4.2 centimeter. So this is your answer. This is the explanation. Okay. In this exercise of previous one, obtain the frequency of revolution of the electron in its circular orbit. Does the answer depend on the speed of the electron? Explain why. So frequency is given by qb upon 2 pi m, and this is one way. Once you know the radius, then this formula is useful. This I also told during the illustration also. If we are not knowing r, then you can use this formula. If you know the r, we use this formula. So velocity is known, radius just we are calculating in last still exercise. So if you simplify it, so you will get 18 into 10 raised to 6 hertz, and that is 18 megahertz. Then does the answer depend on speed? Okay, no, it doesn't depend on speed. So frequency does not depend on velocity. Does not depend on velocity. If velocity is increased, then radius also increases linearly. So increase in speed will balance in increase in circumference. Circumference. So there is no increase in frequency, it remains constant.